Today we're going to be reviewing the skill of simplifying radicals. Okay? What are radicals? People with extreme religious ideas, right? Or extreme political ideas, are those radicals? In mathematics, what are radicals? Well, yes, somewhat. Yeah. We're talking about roots of some type, right? The radical is actually this symbol, okay? The radical is actually that symbol. That's called a radical symbol, okay? What's outside here, the little number that we put out here, let's call it x. That little dude right there is called the what? Does anybody know what that is? That's called the index of the radical. And that index tells us which root to take, right? It's going to tell us we're taking cube roots, fourth roots. If there's no index number there, it's understood to be a square root. All right, so the index is what tells us which root we're taking. All right, so the index of the radical tells us which root to take. Now, what's inside the radical? What do we call the part that's inside the radical? This is the anatomy of a root by Wade Hinton. Yes? Okay, so what is the inside of the radical called? What do we call it? If it's inside the radical, it's called the what? Yes, the radicand. A-N-D. The radicand. All right? So there's three parts of a root, square root expression, cube root expression. There's the radical, which is the actual symbol, the index, which tells us which root we're taking, and the part inside is called the radicand. And all that is vocabulary that helps us discuss things, right? So we can look at a radical expression and I can say, what do we know about the radicand in this expression? And you know what I'm talking about because you know the radicand is the part inside. Okay? Now, simplifying radicals is as simple sometimes as this. What is this problem asking us to do? Take the square root of 9. So inside the radical, our radicand is 9. Our index here is not written, so it's understood to be 2. What is the square root of 9?
3. Plus or minus.
Square root of 9 is 3. And then we've always got this little nagging reflex, right? What did you say? We want to say plus or minus 3. Why do we want to say that? Because we've had that come up, right? A lot of times when we're working a problem and we take the square root, we get plus or minus 3, right? If we're solving, for example, if we're solving x squared minus x squared equals 9, right, we would do what? Take the square root of both sides, and we're told that we have to have plus or minus in our answer right there. So it kind of conditions us incorrectly that the square root of 9 is plus or minus 3. All right? Now, let me clear this up because this is going to be an important concept, not just for college algebra, but for calculus at the next level. How many square roots does 9 have?
1, 2.
It has 2 square roots. What are the 2 square roots of 9? Positive 3, negative 3. 9 has 2 square roots. This question is asking only for the principal square root of 9, and the principal square root of 9 is always positive. Okay, so this is an important fact that you need to know. The principal square root is always positive by definition. Positive. The principal square root by definition is always positive. And that's what this symbol is asking for. The principal square root of 9 is positive 3. The negative square root of 9 is negative 3, but that's a different question, right? We'll ask for that a different way. So keep this in mind. Just like the absolute value of a number, the distance from 0 is positive. The principal square root is always positive. Okay? So we just want 3. 9 has 2 square roots, but this one's only asking for one of them, and it's positive 3. All right, what about this? What is this asking us for? What is this asking for?
Square root of 16a squared.
In other words, what can you multiply times itself to get 16a squared, right? That's what we're asking for when we ask for a square root. And what's the answer here? 4a. All right, and that's exactly what this PowerPoint is going to say. I'm going to clean it up a little bit. I'm going to make it college level. Okay. What if a is negative?
1 over 4.
No, that would be negative exponents, what you're thinking of. But just for example, what if a was negative 2? Okay, so let's plug negative 2 into this expression and see if it's true. 16 times negative 2 squared is equal to 4 times, what's the value of a? Negative 2. What do we have inside over here? 16 times negative 2 squared is what? Y'all don't miss this. It's 64, right? What's the square root of 64? Okay. Now, are these two things equal? Do we have a balanced equation here? These two things are not equal, are they? What is the value of this? Negative 8, and the value of this is positive 8. Okay? So, the 16a squared, the square root of 16a squared is equal to 4a only if a is greater than or equal to 0. Okay. Now, here's where I'm kind of gonna let you be lucky, or let you kind of assume some things. And this is going to come into play a little bit later when we do square root property, when we do the quadratic formula, when we derive the quadratic formula. This kind of comes into play. We are going to assume, and your instructions in your homework assignment are going to say, assume that all variables represent non-negative values. Okay? Non-negative values. If that means x, that the variable is greater than or equal to 0, that this is true. If a is not greater than or equal to 0, then this is not true. So if we don't have the disclaimer, guys, that a, or our variable that we're dealing with, is a non-negative quantity, to make sure that we're doing this correctly, to make sure that we're guaranteeing that the principal square root is positive, we would have to say that the absolute value of 16a squared is 4 times the absolute value of a. Right? And that would make it work. Even if a was negative 2, on this side, if we put, on the left side, if we put negative 2 in, again, we would get the square root of 64. On this side, if we put negative 2 in, we get the absolute value of negative 2. On this side, the right side, we get positive 8. On the left side, we get positive 8, and we're good. All right? So it checks, and we do that to protect the definition of the principal square root. The principal square root, by definition, must be positive. Okay? I'm thinking that's probably a new concept, so y'all make sure that y'all are kind of clear on this. We will deal with this again a little bit later when we are applying some of the important parts of square roots. But for now, we're going to assume that all variables represent non-negative values, and we're just going to roll right through this. Okay? What is the square root of 25x to the 6th, y to the 10th? How would I write this in exponent form instead of radical form? Does anybody remember exponent form for square roots? (25x to the 6th, y to the 10th, raised to the 1/2 power. Right? The square root is the same thing as raising something to the 1/2 power. Now, back to the laws of exponents 2 or 3 lessons ago. How do you raise a power to a power? you multiply, right? 6 times 1/2, 10 times 1/2. And multiplying by 1/2 is the same as dividing by 2, right? So we're taking the square roots of variable expressions. The even exponents are going to work nicely. The odd ones won't work as well. The odd ones we're going to have a remainder. We're going to have something left over inside the radical symbol. For even exponents, everything is going to work out perfectly. All right, so what's the square root of 25? 5. The square root of x to the 6th, half of 6 is 3. Half of 10 is 5, and we're good. All right. Now, again, if we did not know that these variables represent non-negative quantities, we would need these things to be in absolute value symbols just to make sure that they are positive. Okay? If you want to do that, I'm okay with it, but it's not going to be required. It's the concept that's more important than actually doing it. All right? What about the square root of 24? What if the number under the radical isn't a perfect square? What are we required to do to these? Think back to your Algebra 1 skills. Think back to your Algebra 2 skills. What are we required to do with radicals or radical expressions even when the number inside isn't a perfect square? What does it mean to simplify this expression? How do we simplify it? You find the largest perfect square that will divide into it, right? What's the largest perfect square that is a factor of 24? 4? 6 isn't a perfect square, but 4 times 6 will work, right? So what we have to do here, and this is a difficult concept for Algebra 1 students, it's a difficult concept for Algebra 2 students, and it doesn't get any easier here because we're working backwards on these. We're deconstructing the number. So the largest perfect square that will divide evenly into 24 is 4. How many times will it divide into it? 6 times, right? So now we have a product of things underneath the radical. And we can, there's a product property of square roots which says that's the same as the square root of 4 times the square root of 6. We can simplify things that are being multiplied, right? We can separate it into 2 separate radicals. What is the square root of 4? 2. So we have 2 times the square root of 6. That's considered to be a simplified form. It's just a rule. Is it really? Is this any more meaningful than this? It's really less meaningful, isn't it? Can't we quickly approximate the square root of 24? The square root of 24 is almost what? Almost 5. Can you quickly approximate this? No. You can't. Okay, so this is actually really, if we're really talking about things being simple, it's this one that's simple or simplified. Okay, now that is, again, this is a very difficult simple skill. And this is why couldn't we use 8 and 3 or 12 and 2 under the radical for this problem? Because none of those factors are perfect squares, right? We want to use the largest perfect square factor that we can find. All right, so let's do another one. The square root of 72. The square root of 72. Now we want to always find not just any perfect square factor. We want to find which perfect square factor? We want to find the largest perfect square factor that divides it evenly. So maybe we should make a list of the perfect squares. What are the perfect squares? 1, obviously, but that one doesn't ever help us. 4, 9, 16, 25, 36, 7 squared is 49, 8 squared is 64. It's an odd looking 4. Let me undo that. 64. 9 squared is 81, 10 squared is 100, 11 squared 121, 12 squared is 144, 13 squared 169, 14 squared is 196. 15 squared is 225. And you ought to at least be familiar with those 15 perfect squares. At least. Okay? It's really good to go all the way to 20 because they pop up from time to time. 20 squared is 400. So there's just 4 more that you'd need to learn to get up to 20. But those perfect squares are the ones that we're looking for. Now, we want to find the largest one of these numbers, right? So I don't need to look any higher than right here, because 49 is bigger than half of 72. What's the largest number up there that will go into 72?
36.
36 goes how many times? Twice. So the square root of 72 is 36 times 2, right? And then we can simplify the square root of 36. What's the square root of 36? It's 6. And 2 is trapped inside because it's not a perfect square. So the square root of 72 simplifies in radical form to be 6 times the square root of 2. Okay? Good enough? Are y'all remembering this skill vaguely a little bit? It's coming back to you from Algebra 1 and Algebra 2. Square root of 72 is 36 times 2. Now what I'm going to show you down here is what happens if you choose the not largest perfect square. 9 will also go into 72 8 times, right? So we can simplify and get 3 times the square root of 8. But is 3 times the square root of 8 the correct answer? Is it the final answer? These aren't the same, are they? Why are they not the same? We can simplify 8. 8 has a perfect square factor of 4 in it, so we would be required to break it down further. The square root of 4 is 2, so that 2 passes through, and we're left with... Anytime something passes through a radical symbol, it gets multiplied by what's on the outside. So as soon as this 2 comes out, it's going to be multiplied by the 3, and that's where the 6 comes from. Okay? What is this asking us for? It's asking us for the negative square root of 5. This is how they'll ask if they want the negative involved. Okay? The principal square root of 25 is written like this. They want positive 5 when that's written. If they want the negative one, they'll do this. If they want both of them, they'll do that. That's asking for the positive and negative square root of 25. Both roots. Okay? So this is asking us for the negative root, and the negative square root of 25 is negative 5. What's the cube root of 27? 3. All right? Let's talk about cubes. You ought to know your perfect cubes at least through 6 or 7. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343. And the reason I say that it's good to know those is because they come up on standardized tests. Knowing that 216 is 6 cubed will be helpful. It's good, trivial knowledge to have for standardized tests. We need to know these cubes up through 7. 10 cubed is 1,000. You'll see that one also. Right? But that's kind of obvious. 10 cubed is 1,000. So the cube root of 27 is 3. They're asking us what number can you multiply times itself 3 times to get 27, and that would be 3 times 3 times 3 times 3. And the cube root of negative 27. It's negative 3, right? Now this is one difference between odd index roots and square roots, even roots. You can't take the even root of a negative number. It's impossible to multiply an even number of negatives and get a negative. You just can't do it. An even number of negatives will always be positive. So even roots, square roots, fourth roots, sixth roots, even roots have to be positive, what we're looking for, positive. But cube roots are fine. The cube root of negative 27 is negative 3 because 3 negative signs in a product would give you a negative value. So negative 3 times negative 3 times negative 3 is negative 27. And this is going to go to the domain of cubic functions a little bit later when we get to domains and ranges. So what would we do with this? The cube root of negative 8x cubed. cube root of negative 8x cubed. So what was the little trick we talked about a minute ago when we were dealing with square roots to determine if an exponent is a square? It has to be what kind of number? Even, right? If it's an even number, it can be divided by 2, and that means it's a square. For cubes, if it's divisible by 3, then it's a perfect cube. So the exponent is divisible by 3 because taking the cube root is the same as raising something to the 1/3 power. If we can take 1/3 of it, which means it's divisible by 3, then it's a perfect cube. So to take cube roots, you divide the exponents by 3. What's the cube root of negative 8? Negative 2, and 3 divided by 3 is 1. 3 divided by 3 is 1. And so we'll have negative 2x as our solution. No need for absolute values here because cube roots can be negative. Okay? Negative or positive. By definition, a cube root is not defined to be a positive value. The principal square root is defined to be positive, so no absolute values would be necessary here. All right? Let's go. How do you deal with fractions underneath a radical symbol? Anybody? What do you think the answer is here? What's your instinct telling you that the answer is here? Yeah.
Do you multiply it by 1/2?
If there were exponents involved, we would multiply the exponents by 1/2. Yes. Why does that come to your mind? Taylor says she thinks this is the square root of 5 over 3.
Because the square root of 5 can be simplified, but the square root of 1.
So what you're saying is that it's, and this is correct, by the way, but what we're saying here is that we can actually, just like we were able to, if you'll think back just a little bit ago, we had the square root of 24, and I told you guys that's equal to the square root of 4 times the square root of 6. It's okay to break up products and take the square roots of the pieces in a product. And it's okay in a quotient to take the square root of the pieces. This is called the quotient property of radicals. The quotient property of radicals says that the square root or the root of a quotient is equal to the quotient of the square roots. So we can actually separate these two things into two separate problems. Square root of 5 over the square root of 9, and that gives us the square root of 5 over 3 as our final solution. So we are allowed to take square roots of products in pieces. We're allowed to take square roots of quotients in pieces. We can take the square roots of the individual pieces. We cannot do that with sums. You cannot do that with sums. All right, it doesn't extend to sums. What do I mean by that? You can't take this. Let me do one that's familiar. Let's do square root of 16 plus 9. We can't take the square roots of the pieces of a sum. If we did, what would that be? Square root of 16 is 4, square root of 9 is 3, and that would give us 7. But what's 16 plus 9? Isn't that 25, which tells me the square root of this thing is 5. So it falls apart with quotients. With sums and differences. It's good with quotients. It's good with products. All right? Square root of 50x cubed over 2x. Now, this is something else that we could do, just like the sum that we just looked at. It's always good when you can to simplify what's inside the radical before you start taking square roots. Can this radical be simplified? It can, right? 50 divided by 2 is 25. And what do we do with these exponents? What's the quotient rule for exponents? Subtract. So that'll give us the square root of 25x squared, which is 5x as long as x is non-negative, right? 0 or greater than 0. So it's 5x as long as x is greater than 0. If x is not, if we don't know that, then it would be 5 times the absolute value of x, just to make sure that what comes out of there is positive, right? So square root of 5x squared is 5x. So this allows us to take quotients inside of radicals and do it. So we can take the square roots of quotients in pieces, or we can do the quotient and then take the square root. So we can do it either way. The previous example, we took the square roots of the pieces. In this one, we're going to do the quotient and then take the square root. So the order doesn't matter. All right, what is this problem asking us to do? What operation is indicated between these two radical expressions? Subtraction, right? Now, just a few days ago, we talked about simplifying polynomial expressions. And we said that the rule for addition and subtraction is that adding things doesn't change the things, right? So if we have 3x squared plus 2x squared, that's 5x squared. The things that we're adding don't change. What are we adding here? What are we adding? What are these expressions? We're adding square roots of 7, right? 3 square roots of 7 minus 5 square roots of 7. So when we add those radical expressions, just like variables don't change when you add or subtract, radical expressions don't change when you add or subtract. So what's 3 square root of 7 minus 5 square root of 7? Negative 2 square roots of 7. That's right. Okay. And a lot of you guys have that habit. Some of your college professors might get you for saying 2 root 7. Which root? There's lots of different ones, right? So it could be square root, cube root, 4th root, 5th root. So 2 square root of 7, I'm okay if you say it. I'm just kind of saying that's one thing I notice about North Point students. Negative 2 times the square root of 7 is the final answer. It doesn't change. So what's the rule for adding or subtracting variable expressions? When can we add or subtract variable expressions? When they have the same variable and the same exponent, right? So how do we know we can add radical expressions? When they have the same root, they have to have the same index, and they have to have the same, what's the number inside called? Radicand, right? You can only add radical expressions if they have the same index and the same radicand. Okay, we could not add this if it was 3 square roots of 7 minus 5 cube roots of 7. No can do. The indexes are different. You can't deal with that. Okay, all we can do there is take a decimal approximation of this to simplify it. If we leave it in radical form, there's nothing we can do with it. All right, so what do we do when we're adding this? Square root of 5 plus the square root of 5. What's the rule for adding things? When you add things, does their identity change? 1 apple plus 2 apples is 3 apples. It doesn't change what you're adding. So what are we adding here? 1 square root of 5 plus 1 square root of 5, and that's going to give us what? 2 square roots of 5. And the reason that I'm emphasizing that over and over and over again is because this is a mistake that students are prone to making. When you add things, the things don't change. There's just more of them. If you take one of these and you add another one of these, then you get 2 of these, not 2 something else's. Okay? 1 apple plus 1 apple is not 2 oranges. When you add things, the identity stays the same. All right? Can these radicals be added together in the form that they're in? Not in the form that they're in, right? But can we leave our answer like this? Why would this be an improper way to leave an answer? It's not simplified. How do we know it's not simplified? How do we know it's not simplified? Because these radicands all have factors in them that are perfect squares, right? What is a perfect square that will divide into 50? 25. What's a perfect square that will divide into 18? 9. What's a perfect square that will divide into 200? 100, right? So we can simplify the radicals. We have to simplify the radicals. And when we do simplify the radicals, like we were doing earlier, The square root of 50 breaks down into 25 times 2. The 25 passes through the radical because it's a perfect square. Comes out as 5. 9 comes out as 3. And 100 comes out as 10. And now we have three expressions with the same index and the same radicand, and we can combine those, right? 5 square roots of 2 plus 3 square roots of 2 plus 10 square roots of 2 is 18 square roots of 2. Everybody okay with that? All right, so today we've looked at simplifying radicals and adding, subtracting like radical expressions. Your homework is page 46, 13 through 44. This is a little lengthier than some of our homework assignments have been up to this point, but this is a skill that's really sticky. And I will check this tomorrow, so make sure that you have this completed for class tomorrow. Y'all have a great day.